Okay, so let's finish taking a look at this graph. We're going to go ahead and plot all the relative points. To start, negative pi over 4 comma 0, so we do have an extra value to highlight here. So that's the first point. 0 comma 2, pi over 4 comma 0, pi over 2 comma negative 2, and 3 pi over 4 comma 0. So again, this represents only one period of this particular function. If in fact we had wanted to take a look at more than one period, we'd obviously go farther with this. I'm going to go ahead and graph this. Alright, not as precise as I'd like, but I think good enough. Okay, so remember the parent function as well should come into play. Later on I will graph the negative portion of the graph with at least one period denoted, not just with this function but also the parent function, of which I'll go ahead and do again, noting that we're talking about sine. So basic parent function for sine with the sine of 0 to start with, the sine of 0, that's just 0. The sine of pi over 2, that's 1. So these are again your 5 key points. Sine of pi, again 0. Sine of 3 pi over 2, negative 1. I'll scoot that up just a bit. And then lastly, the sine of 2 pi is up at 0. So if you're comparing the parent function, the one in blue, to the red transformed graph in red, you probably can see more now that there is a series of transformations that we already discussed, of which started with a shift left pi over 4. So you're taking the blue function, you're shifting it to the left a fourth pi, or pi over 4. Every point is shifted left pi over 4. It is horizontally shrunk, so the blue function, if you pinch it in from left and right, inward, horizontally shrinking, of course, takes shape like you see here. And then, of course, the last piece here, the A value in this case, because again it was greater than 1, is a vertical stretch. So instead of an amplitude of 1, you're stretching it upward and downward, so your function takes shape as you can see. Like I said earlier, I will be graphing the negative period for both functions as well later. And you'll see that in OneNote, not in a video. So let's go ahead and take a look, continuing on here, part C. So this particular function does have a whole series of things to take a look at. Yet again, I'm going to rewrite the function such that it is very much like what we want it to be. I'm going to move some things around actually as well. I'm going to say negative 0.5 sine of, and I'll factor out that 0.5, that B value, which is not 1. When you factor it out, you'll be able to easily see what, if any, additional transformations exist. So factoring out a 0.5 out of that quantity in parentheses yields this, so x. And then out of the second part there, dividing by 0.5 is the same as multiplying by 2. So that simply becomes minus 2 pi. Okay. So that's hopefully logical in the sense of what then we can depict as far as our B value. Okay, so I'll discuss that in context. Our A value, we'll discuss this, of course, in context. And yes, it'll be the absolute value technically that we're deciphering, and I'll just say 0.5. I'll also point to the negative. The fact that it's negative is important, or at least to distinguish what that's going to do to the function's just general look. This right here is a depiction we need to highlight, or something that we need to highlight, as again we recall from earlier, C divided by B. I do have one other part that I didn't add on, and that's just simply plus 1. I didn't add that on until now. I just moved it, of course, from the beginning. We'll call that our D value. Okay. So here are the nuances for this particular problem, wherein we're again noting kind of from inside out what's happening. Because c over b is 2 pi, because it's x minus 2 pi, that's going to be a shift to the right by 2 pi. If you continue to take a look, kind of inside out, so to speak, 0.5 of your b value as a b value, that will dictate your period. Particularly, again, because all sine functions have a period of 2 pi divided by b, 2 pi divided by a half, or multiplying by the reciprocal, of course, we have that as 4 pi, 2 pi times 2. And because that's technically greater than 2 pi, you're going to have a horizontal stretch. Last problem was a shrink, this one's a stretch. Okay, we have, continuing to work kind of inside out, we have an a value that is less than 1. Technically it's between 0 and 1, but when that's the case, that's a vertical shrink. Okay. The negative in front of the entire function is an x-axis reflection. Okay. And if we continue, the last part, as you can see here, this is just a shift up, this +1 at the end. All right, so yet again, we're going to make our xy table, aka theta y table. And again, noting our period is 4 pi, we'll go from 0 to 4 pi. And notice, again, cutting it in half ends up being 2 pi, cutting that in half, pi, up by 1 pi, 2 pi, 3 pi, 4 pi. Because I'm shifting it to the right, I'm going to be adding 2 pi to everything. You still only need 5 key points when you do it this way. And you may use your calculator. I've been doing quite a bit of the graphing and the analysis in the XY table without a graphing calculator at all. Not needing it at all. It's up to you, though. You can use it anytime you need to. So 2 pi. That's the first. The second, 3 pi, 4 pi, 5 pi, 6 pi. Let's plug it in. If you plug in 2 pi here, you've got 2 pi minus 2 pi, which of course is 0, times anything is 0. Sine of 0 is 0, times negative 0.5 is 0, plus 1 is 1. Plugging in 3 pi minus 2 pi, that's 1 pi, times a half. That's pi over 2, the sine of pi over 2. That's the next increment on the unit circle, as it always will be if we do it in this manner. Sine of pi over 2 again is 1 times negative a half is negative a half, plus 1 is 0.5. 4 pi minus 2 pi, that's 2 pi, times a half, that's pi. Sine of pi is 0, times anything is 0, plus 1 is 1. Plug in 5 pi. 5 pi minus 2 pi is 3 pi, times a half is 3 pi over 2. The sine of 3 pi over 2, again, the next unit circle increment, that's negative 1 times negative a half is positive a half, plus 1, that's positive 1.5. Lastly, 6 pi minus 2 pi is 4 pi, times a half is 2 pi. The sine of 2 pi is 0, times anything is 0, plus 1 is 1. Okay, so we'll get the xy axis again graphed. Yet again, I'm going to graph this with the understanding of possibly only negative, or pardon, positive periods. If we take an extra, I will take an extra step later, but if we do that with regards to you know, how the negative period takes shape beyond, that will be something I can do on OneNote for you. But it again may give you a nice perspective later for sure. So let's go up. There's pi, 2 pi, 3 pi, 4 pi, and I guess if I go up by pi, I might have to condense that down a little bit. And I'm even going to have, whoops, I'm even going to have half increments here as well. So let's do that again. So if I do this, let's go a little bit smaller. 1, 2, 3, 4, 5, 6 pi. Okay. If you can imagine having to put a parent function in on this as well, it'll be a little bit more condensed down, but nonetheless, it's still going to work great. It should. So as we finish here, again, 2 pi is at 1. Here's 1. Here's -1. And then we have, and I'm probably going to need to, if I do it that way, stretch it out just a bit. That's probably going to cause an issue. It will. Okay, so let's condense this down to, later you'll see why I'm doing it this way, but let's condense it down a little bit more, scale it down, such that I can fit in not just 1, but also 2, and also not -1, but -2. Okay, so pi again, 2 pi technically, that's at 1. 3 pi is 0.5. 4 pi is 1. 5 pi is 1.5, so there's why I extended it, as you can see. And then lastly, 6 pi is at 1. Probably don't really need the negative values there below the x-axis, but that's okay. Here's your function taking shape. And there you have it. The parent function should take shape as usual as such. So you'll have the sine of 0, of course, at 0. Sine of pi over 2 is at 1. Sine of pi is at 0. Sine of 3 pi over 2 is at -1, so I did need that negative increment technically. And then back up for 2 pi comma 0. So here's your basic parent function for sine, of which now you can hopefully see from blue to red, you are making those transformations. You're shifting it to the right by 2 pi. You are horizontally stretching it thanks to this b value. You are vertically shrinking it. You are x-axis reflecting it, and you are shifting it up 1. All of those things, please take a look at. There is a line of equilibrium that I haven't had an opportunity to really dig into much at all lately on any of these graphs. I say lately in any of the videos. This line of equilibrium we did discuss in part 1 in our in-class version. The line of equilibrium is literally the line of which you'll have points both above and below, giving you kind of a symmetric view of sorts. I will finish the negative period on one note later. All right, let's finish. Mathematical modeling. Example 4. The average monthly temperatures of a certain city can be modeled by the following. T equals 74.6 plus 12.87 sine of what? 0.52 T minus 2.09, where T is the average monthly temperature and T is the month with T equals 1 corresponding to January. Use this model to predict the average monthly temperature in June. Okay, so if T equals 1 is January, let's think. T equals 6 would technically be the month of June. So we'll go ahead and say T equals, using the equation, 74.6 plus 12.87 times the sine of what? 0.52 times 6 minus 2.09. Now we are not going to graph this. We could. As a matter of fact, graphing it would give us some perspective as to maybe a shift to the right. We've got a b value that may be a horizontal shrink or a stretch. Technically, we can think about that, factoring it out again. An amplitude stretch vertically, and then a shift up. I'm not going to detail that at all in this particular problem. Let's go ahead and do the calculation on our calculator. If you go ahead and type it in, 74.6 plus 12.87 sine of this angle value in radians. I do want you to leave your calculator in radians on most word problems unless told otherwise. The answer in a degree Fahrenheit should end up being 85.63 degrees. And that doesn't say that it's in Fahrenheit, but I believe that should be the assumption if you take a look at how temperatures are in fact going to unit-wise be modeled. So the answer ends up being 85.63 degrees Fahrenheit. And again, I did this in radians. Later, if in fact any problem is to be done in degrees, it will specify very obviously.